Hi everybody, and a very warm welcome to Imperial College if you've not been before, and welcome back if you've been before or if you're a member of Friends. The Friends of Imperial are an outreach organisation attached to the college, and our role is, much as we're doing tonight, to engage the themes that happen in Imperial College and relate those to the public, so that we have a series of, we assure you, non-mathematical lectures, but which describe the science going on in some detail. So if you'd like to join Friends, you're very welcome. You don't have to have come here. You don't have to be in the area. You have to have an interest in science, but you will be rewarded. And the subscription rate is very low. I can't remember the precise number. £20 per year. The programme of lectures that we put on this year are 23 lectures, and we are getting a lot of engagement both from the scientists here at the college and from the public, and we'd encourage you to come along. As ever, with a Friends of Imperial lecture, we are very grateful to the support of Winton Capital, and also for the college for helping us or allowing us to use their facilities. And tonight we're especially grateful because the audio-visual team has come along, and if you do not wish to appear on camera, do not stand where I'm standing now. My position is also affected by the fact they've just run to my car to get some prizes for the quantum bingo. I'll mention that more in a minute. So I will be preserved in my sweaty state for ever. Right, but the theme of tonight's lecture is quantum theory, and specifically the work of the controlled quantum dynamics group here in the physics department. There are in front of me a group of 10 PhD students who are doing their MSc at the moment. And here I go. They are Dave, Alex, Zizhen, Sarah, Andrew, Adam, Henry, Christina, Xiaxi, and Sebastian. And I'd like some applause for that. I can promise you that if everything works right, you're in for a treat. The quantum bingo reference is because each of you will have been given a set of 25 key quantum words that you can cross off as they go through their presentations when you hear them, all except for the first presentation, which is a quantum jargon buster, which goes through those words. So you're not allowed to do it then. But once Alex gets going, you're in business. As I say, part of the work that you do during your PhD is to explain your topic to a hopefully interested but uninformed audience, that being for the PhD students, the people who give them grants. And so what we're doing here tonight is a dry run of the grant process, but it's a great show, and we've got some very good communicators. When you think that these guys are basically 5 years out of upper 6, then you can see what a difference 5 years can make. We know from the past that the most significant contributions to physics are made by people in their 20s. So you can think of this lecture as, rather than having one eminent scientist here to talk to you, you've got 10, possibly soon, to be eminent scientists here. So the value for money from Friends just grows and grows. Now it's time for my reading glasses, because I can't remember points 5, 6, and 7 on the agenda. What I should also say is a warm welcome to the students of St Dunstan's College in Catford. Welcome. You're very welcome to come, not just to this lecture, but others. So the topic of quantum theory is a very, very big one. Try as we might, we can't squeeze all of it into 1 hour. And quite correctly, the CQD team have looked at what is important in terms of turning that theory into technology. So we're not going to talk about Higgs tonight. We're not going to talk about the Large Hadron Collider or dark matter, or even mayonnaise. don't worry. Research that one yourself. What we will be doing is talking about what's weird. And we can't just say that everything's magically weird. Things are weird in a particular scientific way. Now, I don't want to say anything more about that, because I'll soon have my voice encrypted by more knowledgeable people in the front row than I am. So what I'd like to invite you all to do is put your hands together and listen to Dave talk about some jargon busting before we go on to the other presentations. Thanks very much.
Okay, hi guys. As John said, my name's Dave, and I'm a PhD student here in the Controlled Quantum Dynamics group. And actually, before we get onto the jargon, the first thing I wanted to do was just spend a couple of minutes maybe talking you through what day-to-day life is like as a quantum physicist. But then, it turns out Hollywood has beaten me to it. So why don't we start with their take on it? Turns out you don't get to do much time traveling on the Controlled Quantum Dynamics PhD course. And actually, my supervisor doesn't really look like this most of the time. Nor this, nor actually most of the time like this. But in truth, I think there's a reason we're portrayed in this kind of wacky way in the media and by Hollywood. And it's because of this. The impenetrable, complex maths that we have to do day to day. Don't worry, I'm not going to test you on any of this. Well, actually, to let you in on a bit of a secret, we all find it a bit tedious too. And so when we're talking day to day with our colleagues about what we're working on and what they're working on, we'd rather try and avoid lengthy pages and pages of derivations like this. So we tend to talk in this kind of dialect, complete with loads of jargon. Really, we just use the jargon as a shortcut, so we don't have to do the maths. But there's no reason people who haven't done the maths should understand what on earth all of these terms mean. And the trouble is, as quantum physicists, maybe sometimes we tend to forget when we're talking to the uninitiated that you haven't done the maths. And we're not so good at dropping the jargon. So as John said, the first task today is for me to spend a few minutes with you just talking through some of this jargon and making it a little less impenetrable so that you can really enjoy the talks that are to come. The problem is it's going to be a bit boring if I just stand here for the next 5 or 10 minutes and read out dictionary definitions about what these terms mean. So instead, why don't we approach this like physicists and have a look at an experiment. And as we look through the experiment, we'll pick up some of the jargon along the way. Okay, so it turns out the experiment we're going to look at is one that as quantum physicists we've sort of grown up with and we're really familiar with. The purpose of the experiment is this. We're going to look in nature and we're going to try and find a distinctive property of waves and of particles that's going to help us distinguish them, distinguish what we mean in nature by a wave and by a particle. Okay, so let's start with waves, and let's start with a prototype example of waves on the surface of water. So we might start by drawing a diagram, hopefully a fairly intuitive one with some fairly intuitive terminology so far. Okay, the next step is maybe to draw a schematic of the experiment that we're going to go through. So we're going to imagine that over here on the left, we've got some sort of wave generator, a wave machine, that's generating these waves at regular intervals. And each of these lines here represents a crest of one of these waves as it propagates from left to right on the screen. And we watch them as they spread out and hit this barrier over on the right here. Except it's no ordinary barrier. It's got 2 small openings in it, 2 small slits. And those are the only places on the barrier where each of these wave fronts, each of these crests, can pass through the barrier. And when they do, it's almost like we get another source of waves on the other side of the barrier, except now we've got 2 sources, here and here. Okay, so propagating forward, further to the right, what we're going to do is perform a measurement over on the right. We're going to stick a screen down, and we're going to measure the intensity distribution that we see there. And by intensity distribution, I just mean we're going to measure how choppy the water is. So we're going to find there are locations where the water's really choppy, where the waves are really high and low as they pass through this area. And we're going to mark that as an area of high intensity. And at other places, we're going to find that the water's quite calm and that it's not very choppy. And we're going to mark those down as areas of low or zero intensity. And this happens because these sources of waves, as they propagate, the waves can interfere with each other. And the areas where there's high intensity are areas where a crest from one wave, from one source, has met up with a crest from a wave from the other source. And they add together constructively. And you get double the amplitude of the wave at that location than you would have if you just had one wave there. And at other locations where it's calm, where there's zero intensity, it just so happens that there we've got a crest from one meeting a trough from the other. And they cancel each other out. There's destructive interference. So we measure this intensity distribution, and the pattern that we see on our screen is an interference pattern. OK, so that's great. We've identified a property distinctive to waves, this interference pattern. But it's not just distinctive to waves on the surface of water. It's applicable to all waves in nature. And Simon here is showing you exactly that same pattern with light waves. So he's got a laser pen, and he's shining it through a diffraction grating. That's just a wall, a barrier, with slits in it. And as he shines these light waves through this barrier, we get the same interference pattern. We get areas of high intensity, bright spots, interspersed with areas of low intensity, dark regions. OK, so we've identified this property of waves. They can form this kind of superposition that can be constructive or destructive. And we can find that property by measuring an intensity distribution and seeing an interference pattern. So far, I haven't talked about any quantum physics. This is all what we call classical. But I promise you, if you can now understand the jargon in that sentence, you've made your first step as quantum physicists, because it's jargon that's going to come up in the talks to come, and it's jargon that pervades the theory of quantum physics. OK, so let's move on to particles now. And what's the distinction? What do we mean by a particle as opposed to a wave? Well, a wave, as we saw, can be spread out in space. It's completely delocalized, whereas a particle is the opposite of that. It's localized. It has a definite position in space. OK, so let's just take as an example something that's localized in space as a marble, small particle, a marble. And we'll take lots of these, like a beam, and we'll perform exactly the same experiment. We'll fire them towards a wall that has two slits. And we'll look at what happens when we measure the intensity behind that wall. And this time, the result is perhaps a little bit more intuitive. You don't see an interference pattern. You just see the targets accumulate exactly behind those slits. And this is how a particle behaves. So we've now, in nature, worked out an experiment that we can perform looking for this interference pattern. And if we see it, we'll know we've identified a wave. And if we don't see it, we'll know we've identified a particle. OK, so that's great. Hopefully, I've talked you through a bit of the jargon that's going to come up later. But why did I spend so long on this experiment, this classical experiment? And why did I say that as quantum physicists, we're really familiar with it? So far, it's just classical physics. Well, it turns out that when you get down to the quantum realm, so when you start looking at the fundamental constituents of matter, the things that actually make up those marbles, electrons, atoms, neutrons, protons, all these fundamental particles, they don't really behave like that at all. Strange, it turns out that what we see in nature on the macroscopic scale doesn't translate down to the microscopic. When you perform these experiments with, say, electrons fired one at a time at a pair of slits like this, they form an interference pattern, as if they were waves, as if they were completely delocalized. Anyway, I don't really want to spoil the talks that are to come, that are going to delve into this into much more detail. So I'm going to stop there and leave you on that knife edge. The only thing left for me to do now is to declare the game of quantum bingo open. And hopefully you'll join with me in welcoming Alex onto the stage, who's going to talk you through the birth of this strange new theory of physics called quantum.
Right. Hi, everyone. I'm Alex, and today I'm going to tell you about the events leading to the birth of quantum physics at the start of the 20th century. In particular, we'll look at the work of Albert Einstein and Max Planck in understanding the light quantum, or the photon. Now, at the start of the 20th century, the outlook for physics was pretty bleak. It can be summarized by Lord Kelvin, who said, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." It looked like physics was finished. The classical theory at the time described most physical phenomena. However, there were still some problems that classical theory couldn't explain. And this evening, we'll look at one of them in particular, called the blackbody problem. And in fact, it turns out the solution to this problem leads to the new theory of quantum physics. So what is the blackbody problem? Well, first of all, we all know that when you heat a lump of metal, it starts glowing red. And the hotter it gets, the brighter and whiter it glows. The reason for this is that as you put low temperatures, the energy is released as low-frequency red radiation. And as you put more energy in and it gets hotter, the energy is released as a mixture of high and low frequencies, which mix together to give white. Now, in fact, anything with a non-zero temperature radiates. So for example, at the moment, all of you are emitting infrared radiation. And we can use this infrared camera to see it. Now, all this does is it converts the infrared frequencies that you're radiating into visible frequencies that we can see. And you can see that the hotter something is, the brighter it is. So the people in the front row are looking pretty bright at the moment. So what are the properties of this radiation? Well, first of all, to model the properties of this radiation, we have to, to model the properties of the radiation, we have to think of how to model a black body. A black body is something that absorbs and emits radiation perfectly. And in this case, the radiation is just waves like the ones that Dave told us about. Now, we can model a black body with this box, and the walls of the box are at a fixed temperature. And inside the box, there's radiation bouncing around, constantly being absorbed and re-emitted. And in the corner, there's a small hole. And the radiation that comes out of this should have the same properties as the radiation from a perfect black body. So how do we use this to look at the properties of the radiation? Well, classical physics tells us that only certain types of waves are allowed in this box. So you can see that these waves don't oscillate at the walls of the box. And so the allowed waves are only these standing waves of distinct frequencies. Now, each of these standing waves has an associated number of modes. A mode is just a way that the wave can fit in the box. So for example, this low frequency has 3 modes, 3 ways of fitting inside the box. And this high frequency has many more modes. It's not hard to see that as the frequency of the radiation increases, the number of modes also increases. Now, classical physics tells us that each of these modes has the same energy contribution, given by just a constant times the temperature of the walls of the box. So that means that as the frequency of the radiation increases, the number of modes increases, and so the energy contribution of that frequency also increases. So what does this mean? This means that as we go to very low wavelengths and very high frequencies, we have lots and lots of modes, each with a lot of energy. And so the intensity of that radiation shoots up, which is this classical prediction here. In fact, this doesn't tally very well with what we see experimentally. And this deviation is called the black body problem, also called the UV catastrophe, because it happens at ultraviolet frequencies. So what are we doing wrong? Just now I said that classical theory assumes that each mode has the same energy, given by a constant times the temperature. In 1900, Max Planck suggested that actually energy comes in discrete packets, called quanta, and these are kind of like our new unit for energy. He also said that the energy per quantum, per packet, is given by this constant, h, times the frequency of the radiation. This means that the higher the frequency, the larger the packet the energy can come in. Planck also said that the energy of each of these modes, instead of being a continuous value given by the constant times the temperature, in fact comes in a whole number of these packets. So what does this all mean? Whereas before, the energy of each mode can take any value between 1 and 10, now the low frequency modes only come in multiples of 1, and the high frequency mode energies comes in higher packets. So Planck managed to put this together into a radiation law. And using the fact that the energy of the higher frequency modes comes in bigger packets, and also showing the average energy of high-frequency modes decreases, he got this. Whereas before we had the shooting off, now the intensity of very high frequencies decreases. And in fact, this is a fit to data from the cosmic microwave background, which is an idealized black body. And you can see there's a very good fit between the model and the data. So in this case, by quantizing energy, Planck has solved the black body problem. So what came next? Well, in 1905, Einstein said that actually, the energy quanta that Planck introduced, the energy quanta of the radiation, are real particles called photons. And he also suggested that light is made up of photons of a fixed energy. So if you think of light of a particular frequency, it's in fact made up of photons of a fixed energy. And he said that the energy per photon is, just like before, given by a constant times the frequency. So this means energy of a particular frequency is made up of photons of a particular energy. So whereas before you might think of the light from a laser pointer as a kind of continuous beam, Einstein says that you can also think of it as a kind of beam of photons, of packets of a fixed energy. Now, this process of quantizing things into packets is the key to quantum theory. And my colleagues are going to take you through all of the implications of quantizing things like energy and momentum. To finish, I'm going to leave you with a photo from a conference in Brussels in 1927. And this is where the biggest names of the day discussed this new theory and its implications. And you can see there's Max Planck there and Einstein there. And there are actually 17 Nobel Prize winners in this one photo. So we've seen how at the start of the 20th century, physics had been written off by people like Lord Kelvin. However, thanks to the work of Max Planck and Albert Einstein, it became clear over the next 30 years that he couldn't have been further from the truth. Well, thank you for your attention. And I'm now going to hand over to Zizhen, who's going to take you through the interpretations of this new theory.
Hello everyone, I'm Zizhen, and I would like to introduce you to this very important interpretation in the quantum world. It's called Copenhagen interpretation, and it's brought up by Werner Heisenberg and Niels Bohr in the Institute in Copenhagen. This interpretation yields a quite interesting result. It suggests that the whole universe we live in is actually depends on you guys, every one of you. Suggests that when it's sharp out the color it measured, the whole disk will collapse to the color that it measured, like this. Now the disk appears all blue. No, red. Sorry. Now, if another observer wants to measure the color of this disk again, say Candice, she will get 100% chance to measure red, and there is no chance for her to measure any blue or red. This is because the wave function collapse is irreversible. And this is the explanation to the cat. Say the cat is indeed in the superposition state of alive and dead inside the box. However, if we open the box, we are kind of making a measurement to the state that collapse the state to either alive or dead. That makes, classically, we only measure alive or dead because we have already collapsed the wave function. And if we kind of take this concept to a larger scale, to the universe, we can say the universe as a system can be described by a wave function, and you can observe it because you observe it as a daily basis. You can see, you smell, and you hear. And these are all measurements you make to the universe, and this measurement will collapse the universe wave function to what you see, what you hear, and what you smell. And in that case, we can say that the universe you see is completely dependent on you. Thank you, and then let me hand over to Sarah.
Hi everyone, I'm Sarah, and I'm going to take you through one of the weird consequences of quantum theory that was discovered in its early days, called quantum tunneling. So let's just think for a minute. Wouldn't it be cool if we could walk through walls? Not only would you save a lot of time, you'd be able to jump out at people, but also we might one day make it to Hogwarts. So this sounds like fiction, but actually in the quantum world, particles really can walk through walls, and that's something I'm going to take you through tonight. So let's think about a ball in a hill. The ball is in this valley over here, but where it really wants to be is in this deeper valley. That's where it would roll to if the big mountain wasn't in the way. But we all know if you just let the ball go, it's only going to be able to roll up as far as the height at which we drop it, because energy is conserved. So it's just going to roll back down into the valley. The only way for us to get it to the other valley is to give it enough of a push that it can get up and over the top. But things are a bit different in the quantum world. If we've got a quantum particle, such as an electron, and a barrier such as on the nanoscale, then actually, even if it doesn't have enough energy to get over the barrier, it can tunnel through it. So it can appear on the other side, even though it couldn't go over the top. So how does it do this? Well, as Dave was telling us earlier, there's not much of a distinction between waves and particles in the quantum world. So instead of this ball, let's think of a wave spread out through space. So when we make an observation of the ball, it's like collapsing this wave function to a single point, just like Z was just saying. And that's where we observe the ball. And the size of the wave at each point represents the probability of us finding it there. So we can see that if we let the ball go over here, and then we make a measurement, there's a very high chance that when we next look, it's still going to be there. But over here, there is a small part of the wave function. So there is a possibility, a small possibility, that next time we look, the ball happened to be over here. So it looks like it's tunneled through the barrier. So it's this non-locality, or spreading out of the wave function, that allows particles to tunnel through, even when they don't have enough energy. The probability of tunneling is small, but it's greater if the barrier is narrower, as we might expect, or smaller. Or simply if the particle hits it multiple times. The chance of it eventually making it through is greater. So quantum tunneling turns out to be a really important process in nature, for example, in the sun. So the sun wouldn't be able to shine if quantum tunneling didn't occur. The energy in the sun comes from a process called nuclear fusion, when nuclei collide, form a new particle, and release energy in the process. But there's a problem. Both of the nuclei are positively charged, so they'll repel each other, or effectively there's a repulsive barrier between them, keeping them apart. The temperature of the sun isn't hot enough to give these particles enough energy to get over the barrier, so one of them has to tunnel through for them to get close enough to be able to fuse. So even though the probability of tunneling is very small, because there are so many particles in the sun and they're coming into contact over and over again, enough of them do tunnel through the barrier to release the energy we see as sunlight. Tunneling is also important in alpha decay. So an alpha particle will be created inside a nucleus but doesn't have enough energy to get out, so has to tunnel through. It also happens in photosynthesis. And it's recently been thought that it's a process in spontaneous DNA mutation, which leads to evolution or cancer. It even occurs in the way we smell. So there are detectors in our nose that use tunneling to detect the size and shape of different molecules, and this is how we distinguish different smells. We're recently using quantum tunneling in technology, for example, in a scanning tunneling microscope, which uses this to look at surfaces at an atomic scale. If we scan a needle across a surface, then electrons in the surface can tunnel across the gap. And the chance of the electron making this jump depends on the size of this gap. So if we scan the needle across and measure the size of the current, this will tell us about the contours of the surface. And people at IBM have done this and made the world's smallest video. So every dot you see in this is actually an individual atom, which shows you quite how accurate this can be. So we've seen that quantum tunneling is a really important process in nature and is now being used in many technologies. So in the quantum world, particles really can walk through walls, or effectively, there is a quantum Hogwarts. Thanks very much, and I'm now going to pass over to Andrew to talk about the quantum Zeno effect.
A pot of boiling water, a weeping angel, an adversary from Doctor Who, and an ancient Greek. What links these three things? Hopefully, I'll be able to persuade you that the answer is the quantum Zeno effect. So, in about 400 BC, Zeno of Elea wrote some letters to Aristotle in which he posed a few things which he called paradoxes of motion. The most famous one is the paradox of Achilles and the tortoise, which goes as follows. So Achilles is racing against the tortoise, but the tortoise has a head start of maybe 10 meters. But then by the time Achilles has got to where the tortoise started, the tortoise is a bit ahead. And by the time he's got there, the tortoise is ahead still. And so whenever Achilles gets to where the tortoise just was, the tortoise is already ahead of him. And Zeno argues this means Achilles can never overtake the tortoise. He also came up with a paradox called the paradox of the arrow, where he said, if time is made of instants, which can be thought of like a photograph, and in any one instant you can't move, then how can you move? If time is made of instants, you can't move in any instant, you can't move. Motion is impossible, he concludes. If this seems confusing, then I think that's basically the point. We all know that motion is possible. I'm moving now. So there's definitely something wrong in Zeno's argument. It's not that hard to figure out what the problems are. He couldn't have known it, but he was actually right in a sense about the quantum world. So let's say I've got a quantum system that can live in two states. It's currently in state A. If I look at it now, it'll definitely be in state A. But it's going to transition into state B. And the way it does that is it goes through a period where it's a superposition of the two, and then it'll go into state B completely. So what happens if I look at it while it's transitioning, or if I ask Einstein to look at it while it's doing this transition? Well, let's see. Yeah, he collapses the wave function by looking at it. And what will happen there? Well, by looking at these little probabilities, we can see. So there's a bit more of a probability it'll turn into state A, and there's some probability it'll go into state B alternatively if he sees state B. So we can't necessarily say what will happen, but we can say with what probabilities it will happen. Okay, so let's ask Einstein to do another experiment for us. Let's ask him to look at it quite a few times in succession, closely spaced. Let's see what happens now. Okay, so there were a few times where it could have gone into state A or state B, but because he didn't leave it very long to evolve, it was most likely each time it would go into state A. It could, but because he was giving it a lot of observations, there were a lot of opportunities for it to go wrong. It didn't happen to this time. Something that John von Neumann noticed in 1934, which he decided to call the quantum Zeno effect, is that if we asked Einstein to look more and more regularly at it, he'd be giving it a lot more chances to turn into state B, but the probability that it would go into state B would decrease as well. And actually, the more often you look, the more likely it is that it'll just keep going into state A. And he thought this was a bit like Zeno's paradox of the arrow. If Einstein's looking at it every instant, he's not allowing it to move. So yeah, if Einstein is staring at the particle, as he is now, it can't move at all. He's completely arrested its evolution just by virtue of watching it. So what does this have to do with these? We can actually find our answer in the script of Doctor Who itself by asking the Doctor. He says, they are quantum locked. The moment they're seen by any other living creature, they freeze. And now to an extent we understand why. The angel is trying to change its state from state A, possibly over there, state B, nearer me. But if I'm watching it, then by the quantum Zeno effect, I'm stopping it from moving. It just doesn't have the opportunity to evolve while I'm watching it. So that's why, in the quantum world, watched pots really do never boil. Thank you. And now I'll pass you over to Adam, who's going to talk about lasers.
Hello, my name's Adam, and I'm going to talk to you today about lasers, the bright idea that changed the world. So try to ignore the flaming tube. We'll get to that in a second. So what are lasers useful for? I'm sure we've all seen the movies where they're used to blow up planets or interrogate spies, but what can they be used for in real life? Well, they're everywhere in the communication industry. The internet is based upon sending laser light down fiber optic cables, and we can use them to read CDs or barcodes. We use them all the time in science to carry out delicate measurements or to control atoms, for example. And they can even be used in life-changing medical procedures like laser eye surgery. But what you may not have thought about is what actually is a laser, and how exactly does laser light differ from the ordinary light that we see around us every day? Well, consider a filament light bulb like this one. A filament bulb will emit light of many different colors or frequencies, and the waves that it emits will all be in random directions, and they'll all be out of sync with each other. So if you were trying to use this light for any kind of digital communication, it would be hopeless, because any signal you sent would quickly become a jumbled mess of different light waves. In contrast, a laser emits a single frequency of light. In other words, it's monochromatic, and then the waves that it emits are all in sync with each other, and they're focused in a particular direction. And we call this a coherent beam, and it's much easier to control and to send signals with this light. So how do lasers work? Well, I'm sure we've all seen pictures of atoms with electrons orbiting around a central nucleus. But what Niels Bohr realized in 1913 was that the electrons can't take just any orbits around the nucleus. There's this discrete set of quantized orbits that the electrons are allowed to take, each with their own fixed energy level. And while an electron can't have an energy somewhere in between these two levels, they can jump from one level to another by absorbing or emitting a photon. And crucially, the frequency of this photon has to correspond exactly to the gap in energy between these two levels. The next piece of the puzzle is a process called stimulated emission, which was first proposed by Albert Einstein. He realized that if you shine light onto an atom at one of these special frequencies corresponding to a gap between energy levels, you can force the atom to emit another photon of exactly the same frequency. And this photon can go on and hit more atoms and cause more stimulated emission, leading to a sort of chain reaction. And crucially, the incoming and the outgoing light waves are exactly in sync with each other. The next thing to think about is what happens when we have light trapped inside what we call a cavity in between two mirrors. Well, when a wave is incoming and incident on a mirror and gets reflected, the incoming and reflected waves can interfere with each other, adding up in some places, like you see here, and cancelling out in others. And this is just like the interference pattern that Dave described to you earlier. So what happens when the frequency of the light is exactly right is that these points of maximum and minimum interference don't move in space, and we get what's called a standing wave, where the whole wave oscillates up and down at the same frequency, but doesn't move from side to side. And we see this all the time in physics. For example, if you were to pluck a guitar string, you form a standing wave between the two fixed ends of the string, and then the frequency of that wave is like the pitch of the musical note that you hear. And we're demonstrating this here with what's called a Rubens tube. There you go. So you send pressure waves through this flammable gas inside the tube, and we can vary the frequency. And whenever the frequency is just right, so that the length of the tube is an exact number of wavelengths of the pressure waves, then we see these standing waves. So wherever the gas is oscillating the least, the flames burn brightest. So we can actually see the standing waves traced out by the flames wherever the frequency is just right. Thank you, Simon. OK, so how do we put all this together to make a laser, as was first done by Charles Townes in 1951? Well, we put a bunch of light-emitting atoms inside a cavity between two mirrors. We stimulate them to get them to emit light. And so if the frequency of the light that they emit is exactly the same as the standing wave frequency of the cavity, you get a resonance between the two of them. So the more light there is inside the cavity, the more stimulated emission you cause. And then the more stimulated emission there is, the more light gets produced. So it's like a sort of feedback effect, where you get more and more amplification of light. And eventually you get this extremely bright beam, but crucially, all the light waves that are emitted are exactly in sync with each other and of the same frequency. So this makes it very useful for experiments. So to summarize, the light in the laser comes from stimulated emission of atoms inside a cavity. There's a resonance between the atoms in the cavity, and you get an extremely bright, coherent beam coming out. And there's a huge range of applications for this in everyday life already. They've even been used to measure the distance to the moon by seeing how long it takes a laser beam to go and get reflected back. But there are a huge promising range of applications for future science. For example, they can be used to trigger nuclear fusion, or we even use them to control the atoms inside our quantum computers. So thank you for listening, and I'm going to hand you over to Henry now, who's going to talk about quantum encryption.
Hello, everyone. I'm going to be talking about quantum encryption. So let's start with classical encryption, which is used a lot today. Classical encryption is where you have some information or data which you don't want anyone else to see. So what you do is you encrypt it so that no one else can see it. And this is very useful for a wide variety of applications, such as banks and online shopping, both using the transfer of money. You don't want anyone else to know your credit card details, so you encrypt them, and they can't. And so you can secure emails and phone conversations as well, so that no one else can see the things you are sending to other people. This is very important for governments who have sensitive information which they want to send. And also a lot of our critical infrastructure, such as all of these things here, is controlled by computers. And if you can hack into those computers, you can destruct all of this infrastructure. And one of the ways in which you prevent this from happening is by encrypting all the communications which these computers use. And that then helps prevent the hacking. So this is all the things which classical encryption is currently used for, amongst others as well. So now quantum encryption. Why do we want it? Well, for starters, RSA, which is the current classical encryption protocol, is going to fail as soon as anyone builds a large enough quantum computer. And so therefore, we will need a new way of encrypting all of our information if we don't want anyone to see it. And so quantum computing is based on two fundamental concepts. First of which is the no-cloning theorem, which says you cannot make a copy of quantum information. And the second one is the measurement problem. So we'll start with no cloning. This says, so you can't make a copy of quantum information. What this means is if I have a key, a quantum key, with which I'm going to unlock my encryption and see the information inside. So I have one of these keys, and I want to send it into a quantum photocopier, and out will come two keys, each of which could unlock my data. Now this is impossible because this quantum photocopier does not exist. It is impossible to copy quantum information and then to have two of them at the end. So if I have a quantum key, which I'm using to encrypt my data, I can be sure that there is only ever going to be one of those quantum keys. Because if I start out with one, you can't copy it, and so there can never be two. This means if I have the only quantum key, no one else can get into my encrypted data, which is obviously exactly what you want. So the second piece of information we need is the measurement problem. The measurement problem says that measuring a quantum object removes some of the information about it. And this means that if you were to have a quantum key and you were to measure one of its properties, you could no longer measure the other property. And the analogy I'm going to use here is an egg, which has been found in Jurassic Park. And we have two scientists. And one of them is a bit weird, and he wants to know what color the yolk of this egg is going to be. And the other scientist, he would like to know the height of the dinosaur which is going to hatch from this egg. Now, the question is, can both of their questions be answered? For the first one, you would have to break open the egg and have a look to see what color the yolk was. The second one, the egg would need to hatch, and then you need to get the dinosaur and measure it to see how high it was. And obviously, you can't do both of these at the same time. So this is the measurement problem. If you were to measure the color of the egg, you would not be able to see how high the dinosaur was, and vice versa. So those are our two principles. I'm now going to show you how they can be used to encrypt data with a fun analogy. So I'm not going to throw lots of maths at you and bits and computer science stuff, because that's complicated and boring. So instead, we're going to have James Bond here, who is trying to communicate with his favorite Bond girl. And this is a villain called Engelbert, who is trying to intercept the communications. And in this analogy, we're going to have invisible ink of two colors, red and blue. So you can only look at one of these colors at once. So if you try to read a red message, you cannot then read the blue message, and vice versa. This is the measurement problem. Once you know one thing, you cannot know the other one. And we're also going to split up the message we're going to send and add some garbage words to it. So for instance, the money is in the car. We split this message up and added some extra words in there, the garbage words. And the reason we do this is so that we can send the message little bits at a time. We don't want to send the whole thing at once, because then if something goes wrong, the villain will have the entire message, which is not what we want. And so the villain here, if he is to get the entire message, he has to intercept each and every one of these little messages without Mr. Bond noticing. Because if Mr. Bond realizes that some of these messages have been intercepted, then he will stop sending the rest of them, and we will never get the entire message. So he has to intercept them without anyone noticing. So now on to the algorithm. Mr. Bond is going to write two letters on his bit of paper. These are the different colors of ink. And this is one of the garbage words which I mentioned earlier. So we don't mind what happens to these at all, because they're garbage. And this is invisible ink, so obviously it vanishes. And then he sends this off to the Bond girl, and it gets intercepted by the villain. The villain decides to read the red message and sees a P. Now the message vanishes, and he can no longer read the blue message. This is the measurement problem. And so the villain knows one of those letters, but not the other one. He then creates a new message, and he writes the red P because he knows what that one is, but he doesn't know what the blue letter was. So he makes one up. And obviously it's wrong because there are 26 letters. So these vanish again. And he then sends it on to the Bond girl because he does not want to know that anyone to know that he has read the message, and so it must appear that he hasn't. Now the Bond girl, by chance, decides to read the blue message, and she reads a Q. And so this is a garbage message, so she can send that over a phone. It doesn't matter who hears. She could shout it across the street, and it wouldn't matter. If someone gets this information, nobody cares. She texts Mr. Bond, the blue one was a Q. And Mr. Bond says, I sent her an F in the blue ink. What on earth is going on? Somebody must be reading our messages. I'm not going to send the rest of my communications because they're being intercepted. And so he doesn't. And then the villain never gets the message. And that is the basis of our quantum encryption algorithm. Now, some of you may have seen a flaw in this. Engelbert thinks he has as well. And so what he's going to do is he's going to get this message which he has, and he's going to copy it and then read the red letter on one message and the blue letter on the other message. And then he knows both bits of information. He can perfectly reconstruct it. So this is another message with both of these letters on it, which you can then send on to the Bond girl, who will be none the wiser. Now the problem with this is the no cloning theorem, so you could not copy this bit of paper and then read both of them. That's not possible. And of course, the other bit of theory we had at the start was a measurement problem. So if you have a way to get around this encryption algorithm, it won't work, and it will either be for this reason or this reason. Obviously, the real quantum encryption algorithms don't use invisible ink and bits of paper. They're a lot more complicated and use tiny atoms and bits of light and things like that. But they rely on these basic principles to work. Thank you very much. Next talk will be on quantum computing by Christina.
Hello, everyone. I'm Christina, and today I'll be talking about quantum computers. But first, let me motivate why classical computing is not enough. Take this problem, the Tube Challenge, where people attempt to visit all stations on the London Underground in the shortest amount of time possible. Now, assuming this doesn't happen, we want to find what the best route is, and we could do that by checking for each possible solution and brute forcing it on a computer. If we did that, then we'd see that for each station that we add, the number of routes that we'd have to check grow fast, very fast. And by the time we hit all the 270 stations, the time needed for the computation to finish would take longer than a lifetime. So that's not good. And there are many problems of this kind of complexity for which an efficient classical algorithm that solves the problem exactly doesn't exist. One way of tackling these sort of problems is by thinking of new ways to define what a computer actually is. And this is where quantum mechanics comes in. So a quantum computer would use things like superposition, entanglement, in order to perform computational tasks. As you all know, a classical computer uses bits, which can take the value of 0 or 1. By analogy, a quantum computer uses quantum bits, or qubits, which can not only be a 0 or a 1, but they can be both 0 and a 1 in a superposition. Let's illustrate this by sort of thinking about the duality principle. So if instead of a 1 and a 0, we had like two waves, and we add them up together, we get something that's kind of like half a 0 and half a 1, a qubit. And if we were to measure this, we'd see that half the time we get a 0, and half of the time we'd get a 1. Now, there are two important things to remember about quantum computers. First, they use qubits that are in a superposition. And second, the only way of getting meaningful information out of them is by measuring those qubits. And that destroys this delicate superposition. In a lot of popular science articles, a quantum computer is often described like this massively parallel classical computer that checks for each solution simultaneously. But this is not an accurate description. A quantum computer, we can view it more like a sort of a black box. And if we were to open it and look inside of it, we'd measure it and would destroy this delicate superposition I've been talking about. Hence, the quantum computer wouldn't be able to finish all its computational tasks and give us the correct answer. We would get some random outcome that's pretty much meaningless. But how do quantum computers actually solve problems? Well, quantum mechanics tells us that a qubit can not only be in an equally weighted superposition of a 0 and a 1. These weights can be pretty much anything. They can be negative numbers and even complex numbers. They're called amplitudes, and they're the ones that dictate what the probabilities of different measurement outcomes are, as you can see over here. Now, if we had 2 or more qubits, then these amplitudes could sort of interfere with each other, and it can lead to cancellations and reinforcements. And this is how a good quantum algorithm uses. So a good quantum algorithm, what it would do, it would sort of exploit this, the structure of the problem in order to manipulate these interferences such that only the amplitude corresponding to the wrong measurement outcomes cancel each other out, and we only get the computational path that leads to the correct answer. Now, developing quantum algorithm is pretty difficult because of this sort of
a very precise manipulation. But there have been developed, and the first example of such a quantum algorithm has been developed in 1994 by Peter Shaw over here. And it solves a factorization problem. So it looks for prime factors of a given number, like this one over here. This is the largest number that has ever been factorized on classical computers working in parallel. And if you were to do it on your computer at home, it would take about 2,000 years. But a quantum computer using Shaw's algorithm would only do it in 30 seconds. That's brilliant. But so you can see that classical computers find this problem very, very difficult. And in this difficulty, most of our current cryptographic protocols rely on. If we were to have a quantum computer, we could break all of these. But actually, people would come up with new ideas of encrypting data, like Henry talked to us about. So actually, what we'd use a quantum computer for, we'd use for other things, like simulating quantum physics, which is difficult for a classical computer, because for each extra qubit that we add, we have to double the amount of classical information needed in order to describe those systems. And this is an important application. And it's not as trivial as you might think that quantum computers can simulate quantum physics efficiently. It has been proven rigorously, but only in 1996 by Lloyd. So it's an important problem that can lead to major applications from chemistry to material science. It could solve things like the protein folding problem, where we look for the ways in which a protein folds into its most stable configuration. And this is important because it gives us the promise that quantum computers could lead to understanding how genetic diseases occur, and maybe even developing new drugs. Thank you. And I'll hand over to Shashi, who's going to...
You put your hand up, who? Okay,
the end. Is that vertical or horizontal?
It's horizontal.
Oh, okay, that one's dead.
Okay.
Oh, we've got two more. All right, brilliant.
Okay, so we've got three so far.
Double up there.
You good?
Okay, we should be all right now, as long as no one else gets it.
We've got two more presents to do. Just don't add any new words.
Actually, got some good ones.
So, hello guys, my name is Yashi. I'm another PhD student here. Today I'm going to talk about real world concept of matter wave, and it might be something which will help you win a football match. So, in a free kick situation, there's sometimes a war of people, and I can't think that people just a bit afraid of being shot in the face. Anyhow, let's imagine the worst case scenario. Let's imagine we have Oliver Kahn as our goalkeeper, but we have David Beckham as our kicker. And instead of using a wall of people, we use a real wall, which also has two gaps in between. So we let David Beckham kick the football one by one through the two gaps, and Oliver Kahn can basically easily guess the position of the ball after the wall, which is actually not really great. So suppose that David Beckham is a quantum physicist. So he replaced the ordinary football by a quantum ball. So the only difference between a quantum ball and the ordinary ball is that one cannot know through which hole the quantum ball flies through. So we can somehow imagine it as if there are kind of clouds sitting in front of the wall. So if David Beckham somehow kicked the quantum ball also one by one into the cloud, the position of the quantum ball shown after the wall will be totally different than the pattern we see for the ordinary ball. So what's happening actually here? This has something to do with wave and the particle concept, what my colleague Dave mentioned before. So in the classical world, the particle and the wave concept are basically two completely separate concepts. A particle has a defined position in space, but the wave is delocalized. One can tune its frequency, also its amplitude. But in quantum world, those two concepts are really mixed up. In 1920s, a French physicist called Louis de Broglie once mentioned that a single particle can also behave like a wave. He basically addressed to everything a wavelength. He actually became so famous because of that, so that people today refer it to the so-called de Broglie wave or the matter wave. And its wavelength is depending on the mass and the velocity of the object. So yeah, let's just put some random number into this equation just to get kind of feeling. Let's take myself as example. With my exact weight of 75.145 before lunch, and suppose I can run like 20 kilometers per hour, and my wavelength would be 0.000 with 3601 meters, comparing with the electron traveling with a speed of 225,000 kilometers per second, which only have 3 picometer, which still have 12 zeros. But we're slowly getting to a regime where people now, they can actually measure it. I know those numbers are really, really small, but if a particle really behaves like a wave, even with such small wavelength, we should be able to see them interfere, right? As a kind of proof. So let me shortly remember you what I mean by interference. If you create a water wave and let the water wave propagate through two slits, and at the very end of the lake, you will see a kind of very dark, bright pattern as here. Yeah? So if a particle really behaves like a wave, so we should be able to see the exact same pattern here. Now let's go. Oh, so yeah, and those patterns are actually created due to the constructive and destructive interference. This is when the water waves cancel each other out or when they add them up. So let's go back to our David Beckham free kick experiment. Instead of using a quantum ball, we replace it with some dye molecule. And we send those molecules one by one in through those two slits. And this is actually what people observed after those two walls. As you can see here, the dye molecule shows the exact same pattern as we just observed for water. So the molecule indeed behave like a wave. Of course, those molecules are not the only objects showing quantum interference. Over the last 80 years, the size of objects showing quantum interference have increased from few atoms to few hundred of atoms. And maybe one day we will be able to make a real football interfere and win that football match. And thank you. And I will pass the talk to my colleague Sebastian for the late choices.
No other bingo? No? Is this working? So hi, I'm Seb, and I'm yet another PhD student here at Imperial. And my research is focusing on building light bulbs that essentially spit out single photons at a time, single quantum particles of light. So I would like to take this talk to tell you how weird single photons can be. So by now, everyone would have told you that waves are particles and particles are waves, that are single concepts merged together at the quantum level. Because let's face it, that's our favorite topic of conversation as quantum physicists. But some of you probably thought that was completely insane, and I surely did. So let's try to back up a bit and try to come up with a good explanation of how this came to be. So Niels Bohr, a very clever man, always refer to Niels Bohr when you have a problem in quantum mechanics. He once said that you cannot observe both the wave and particle properties of a quantum object at the same time. You have to choose a particular apparatus, a particular experimental way of doing it, and this determines if the particle is going to behave like a particle. The quantum object is going to behave like a particle or a wave. I always get these mixed up. So here we are. There's our photon, our quantum object, and it's heading towards a measuring box, and its box is set to a wave, and the photon knows this, so it transforms to a wave, goes in there, and we see wave effects. If the box was tuned to particle, then the photon would have transformed to a particle, go in the box, and we'll see particle effects. But this already raises one loophole, and this is, well, how does it decide? Where does it decide? So let's fix this now. This is a beam splitter. And waves and particles behave rather differently when they encounter this simple piece of optics. Waves essentially split into two daughter waves that propagate along two different paths at the same time. But particles, by their very own nature, have to choose one path along which to travel. And they choose randomly which one they want to go through. So this apparently defines the moment where the photon has to decide. Either it travels along both paths as a wave or along only one path as a particle. So there's one experiment people do with single photons. And this is rather simple. This is just one beam splitter and two detectors. And I'm going to let you appreciate that the photons do not interfere there at the crossing. But what we essentially get with this experiment is that detectors click only once at a time. They never click both together. And this is because the photon chooses only one path along which to follow. So we say that a photon behaves as a particle. And this is pretty much like asking the question, which route did you travel along? And the photon always goes either path 1 or path 2. It never goes both paths. There's another experiment. And it's very similar to the first one. The only thing I did there is put another beam splitter here at the crossing. But this has a drastic effect. Now the photons follow both paths, interfere at the second beam splitter, and we get a nice interference pattern at the detectors. So in this experiment, photons behave as waves. And this is like asking the question, did you travel along both routes? And the photon always goes, yes, of course, there's an interference pattern to prove it. So now you say, well, if I understand what he's just said, then if I put the top experiment in front of a photon, this is like saying, are you a particle? And the photon always says, yes, of course, and he behaves like a particle. But now if I put the second experiment in front of the photon, now he says, they're not going to fool me. I know this is a Mach-Zehnder interferometer, so it dresses as a wave and behaves like a wave. And this is a nice way of understanding the statement of Bohr, that it is the measuring apparatus that determines the behavior of the quantum object. But now there's another clever guy called John Wheeler, and he once asked this question. He said, look, you don't have to choose between the top experiment or the bottom experiment before the photon passes the first beam splitter. So now we keep both apparatus behind our back, and when the photon comes to the beam splitter, he says, wait a minute, what is the question they're going to ask? And Mr. Wheeler says, I'm not going to tell you, pass first, and then I'll decide. So there's a cartoon of it. For example, the photon comes to the first beam splitter. We're going to pretend we're going to ask the question, which path? And in Bohr's story, now the photon has to assume a particle life. So it travels towards the measuring apparatus. But now we make the random choice of changing the apparatus, of leaving the apparatus the way it is, or changing it by just introducing one beam splitter. So now, if we had made the choice to change the question, what would happen? Would the Mach-Zehnder interferometer fail? Would we see an interference pattern? So this experiment was done only very recently in the lab on an optical table. And this is because if you think carefully about it, photons literally travel at the speed of light. Therefore, you need a very long optical path to give your electronics the chance to make this random choice before the photon arrives. And it's very hard to work an interferometer with single photon sources on these kind of length scale. But nonetheless, it has been done by Monsieur Aspect and graduate students that probably did most of the hard work. And this is what they found. So if we separate the cases from which the beam splitter was introduced to the one where it wasn't, this is what we see. In the events that the beam splitter was introduced, we get a nice interference pattern, which is characteristic of a wave-like behavior. And we say that the photons behave like waves. But if the beam splitter was not introduced, then we lose the interference pattern. And we can also say that there's close to zero coincidence counts at our detectors. So what can we conclude? Well, regardless of what apparatus we had first, when the photon arrives at the first beam splitter, it seems like it forgot what state it was in to adapt to whatever apparatus we had at the end. And the accepted picture is that the photon remains a wave and a particle throughout the experiment until it is measured by the detectors. But I just like to think that photons have very short memories. Thank you.
I don't know if the microphone's working. Yeah, good. I don't know about you guys. I really enjoyed that. I know how much hard work has gone into all of these presentations. And I know what a learning exercise it has been for everyone involved, and even on the night to get the Rubens tube working. It was a huge sigh of relief when that happened. So could you put your hands together one more time for all 10 students, for Simon, and for the audio team who've been filming the demonstrations. Thanks very much for coming along. Hope you have a safe trip home, and the students will be outside to answer all the questions that you've got.